All right, everyone, let's take a look at what we've got here. This is a 7.2 counting our way to probabilities. In the first one we're faced with, and we're going to evaluate this expression. We're going to express our answer in as a fraction lowest terms or as a decimal rounded to the nearest thousandth. I like to leave them as fractions myself, but check out our notation here. Now, what we have here is a combination divided by a permutation. We'll be talking about these combinations and permutations quite a bit over the next few sections. They're not super hard to, as long as you understand what's happening. A combination basically, it's when you're figuring out how many combinations you can have given a certain amount of people or entities or whatever, assuming that order does not matter. Whereas a permutation is the same thing, where you're doing some kind of a combination except order does matter. And we're going to see that here in another problem or two. But let's take a look at these formulas here. The formulas for, and I would give this to you on the final, but for a combination, it's n factorial over r factorial times the quantity of n minus r factorial. And then your other guy for permutation, it's almost the same thing except you don't have that extra r factorial in the denominator. So what is a factorial? Maybe we should back up and answer that question. Well, a factorial, if we look at n factorial, for example, it's basically n times n minus 1 times n minus 2 times n minus 3 times all the way down to n minus n. Well, what does that mean? Okay, if we just use an example, let's go with 5 factorial. It's just 5 times the number just below it. So 5 times 4 times 3 times 2 times 1 until you get pretty much to 1 and multiply that all out and you've got it. All right, now that we have that established, let's take a look at this problem. We're going to take 9 choose 3 for the combination of 9 choose 3, and then the permutation of over, well, it's that combination over the permutation of 9 choose 3. So how does that set up? Well, the long way of doing this, it looks like this. Okay, just bear with me here. Okay, I've got an easier way to do this here in a second. 9 choose 3 is going to look like this using our formula of 9 factorial over 3 factorial times the quantity of 9 minus 3 factorial. And then downstairs, we've got 9 factorial over 9 minus 3 factorial. So the 9 minus 3, of course, that's 6. So now we're looking at 9 factorial over 3 factorial, 6 factorial, all that over 9 factorial over 6 factorial. So you got a nice little complex fraction going on here. Now, if we invert and multiply this bottom fraction, we're looking at 9 factorial over 3 factorial, 6 factorial times 6 factorial over 9 factorial. And the 9 factorials will divide out, as will these 6 factorials, leaving you with 1 over 3 factorial. So if you want, when you hit this kind of a problem, you can just skip all this other stuff and just say, you know what, it's 1 over 3 factorial because all of this other stuff divides out anyway. And of course, 3 factorial is 3 times 2 times 1. Your answer is 1 over 6. Now, that is one approach to this. Let me try something out with a calculator. You might be interested in this. So what I'm pulling up here is let's see if I can, give me a second. Let me readjust these windows here. So what I've got here is a calculator here. Yeah, nuts. Give me another second to expand my window. All right, that's better. So this is a TI-30S XS. Most Texas Instrument calculators will run similar to this. A graphing calculator is going to be slightly different still. But there's a feature in here I want to check out. Watch this. So I'm going to do this problem here on a calculator. 9 choose 3 on a combination over 9 choose 3 on a permutation. So let me do the combination first. I'm going to go 9. And then this PRB button, I'm going to click that. And look what pops up here. I've got permutations, combinations, and factorials. So since we got a combination here, I'm going to go ahead and choose 2. That tells me that I'm going to deal with a combination. And we're choosing 3, so I'm going to type in 3. And you know what? I just realized something. I probably should have had that in parentheses, that whole thing. Otherwise, I'm going to run into problems. So let me delete all that and clear my key history. So let me start with parentheses. 9 choose 3 and close that parentheses. And now I'll divide by, and let me go in parentheses again, 9 and go with this probability button here. And this time it's a permutation, so I'll type in the 1 there. And I'm choosing 3 again. close my parentheses, and voila, I've got a decimal. So what is that going to be as a fraction, you ask? Well, if you want, you can write your answer, by the way, here. It said we can write as our answer as a decimal, but how would we convert that into a fraction? Well, if you really wanted to do that, I guess what you could have done was just do the 9 choose 3. Like that. You get 84, and then you do 9 choose as a permutation 3. You get 504. And if you wanted to show off with your calculator, I suppose, you could do 84 and then this little fraction button here. Look at that. It's going to turn this guy into a fraction for us. And it should reduce for us. There you go, 1/6. Boom. For you calculator lovers out there, I dedicate this problem to you. All right, the second one, the college's lacrosse team will play 20 games next spring. Each game can result in one of two outcomes, a win or a loss. Find the total possible number of outcomes for a season record. Well, let's think about this for a minute. If it's one game, we're talking about a win or a loss, too, correct? Now, if it's 2 games, you've got 2 games of which you have a win or a loss, so that's 4 outcomes, right? Now, if you got 3 games, then you've got to look at something where you've got a win and a loss, or you could have straight wins, and you could have 2 wins and a loss, or you could have a win and 2 losses. Long story short is you're going to look at 8 outcomes, right? Or 8 possibilities there. So, what's happening? Well, what we're doing is we're taking 2 and we're raising it to whatever power is, depending on how many games we're talking about. So in this case, it's 2 to the 20th. That's all you're doing. So just take 2, and depending on your calculator, you want this little power button thing. 2 to the 20th. There's your answer right there. Should we check out, see if we're right? Right. 1048576. Ta-da! We nailed it. All right, now this next one's an interesting one. Shannon was born on basically September 9th, 1990. How many 8-digit codes could she make with the digits on her birthday? So how does this one set up? It's going to be different than with anything we've seen so far. By the way, this is fair game for a final exam or a midterm. I think it's on the midterm. I can't remember. It's on an exam. It's fair game. So here's what's happening. You've got 1, 2, 3 zeros, right? So call that 3 factorial, representing the zeros. You've got 4 9s. We'll call that 4 factorial, representing the 9s. There's only 1 1, so we'll call that 1 factorial, representing the 1. And you've got 1, 2, 3, 4, 5, 6, 7, 8 digits. So that's 8 factorial. Now your setup is your total over all your different options. So 3 factorial, 4 factorial, 1 factorial. And that's what you're multiplying out. You're looking at a... So I took a minute and paused the video to finish this one out. Again, we're looking at 8 factorial over 3 factorial, 4 factorial, 1 factorial. Now, one way to do this, to solve this, would be to take this 8 factorial and break it down so that you're looking at 8 times 7 times 6 times 5 times 4 factorial, and just bring it down far enough so that this 4 factorial will divide out with this 4 factorial, and all you're left with is the 8 times 7 times 6 times 5, which we see over here, and this 3 factorial, which you can write as 3 times 2 times 1. And then, by the way, 3 times 2 down here in the denominator, that's a 6, which divides out with this 6, leaving you with 8 times 7 times 5, which is 280. So that's another one. That's one way of solving this thing. If you really want to look at another approach that's quicker, let me throw this idea out here at you. Let's use our little handy dandy calculator again. And we could just probably calculate it straight off of this step right here. Let's take our 8 factorial. And remember that one probability button where we could see our 3? Option 3 on the probability, that gives us our factorial. Now we'll divide that by, and we're going to need parentheses. And we'll put in our 3 factorial. This is kind of clunky for me because I'm using a calculator. 3 factorial. And let's see if this works without me having to write a multiplication sign in there. I'm not sure. We'll figure it out. Times 2 factorial. And then times 1 factorial if you really want to put it in there. I don't have to, but because 1 factorial is just 1. And we'll close our parentheses, and let's see if that worked. It liked it. 3,000. Whoa. Okay, something's up. Hang on just a second. Haha, I goofed. Sorry, so I found out my mistake. I put 2 factorial when I should have put 4 factorial. Duh. Alright, let's make that equal. There it is, 280. I got it. So you can use a calculator to figure out your answer a little quicker if you want to go that route. But it's totally up to you how you want to work it, alright? Now this problem here, we got 42 factorial divided by 21 times the quantity of 45 minus 6 factorial. I'll leave this for you to figure out. What I would do is go ahead and subtract this to make it 39 factorial, and then change this 42 factorial so you have 42 times 41 times 40 times 39 factorial. The 39 factorials divide out, and then just take your leftover numbers and number crunch from there, and you'll have it. This problem, we have a word problem. So you got the Hoffmans, they're planning their next family night. They always have dinner out somewhere, and then they do something fun together. There are 2 adults and 3 children in the family. Each family member is allowed 3 meal suggestions, and each child is allowed 3 activity suggestions. Assuming no family members choose the same thing, how many different family night possibilities are there? Give me a second to let me set this up. Alright, sorry guys, I traded up this problem for a new one just because I made sure I knew what was going on here. So this one's, they changed the numbers. Hoffman's planning their next family night. They always have dinner somewhere. They do something together. There are 2 adults, 2 children. So that's a total of 4 family members here, right? And they got 3 meal suggestions. So 4 times 3 gives you 12 options for the family meals. Now, in addition to that, I probably shouldn't use the word addition, but oh well. The children, each kid gets 3 activity suggestions. Now, remember, there's 2 children, 3 activity suggestions. So 2 times 3 is 6. And then after we get this 12 and the 6, you just multiply them together, and there you go. 72 would be your answer for this problem. All right, and if I'm not mistaken on this one, you just multiply the 17 and the 8 together because you're looking at 17 pair of jeans. She's going to pack 8 of them. So if you just multiply them, you should have your answer. I think I did this in advance. Let's see. Yeah, 17 times 8, 136. Should we check it and see if we're right? We are not. All right, hang on. Let's see what we did wrong. Now, this is what I get for working under pressure. I figured it out, I think. So let's get rid of this 136. It's not a simple matter multiplying this together because it's a combination problem. She's got 17 pair. We're going to choose 8. And order doesn't matter, so this will be a combination, not a permutation. So yeah, let's get rid of this. So let's go with our 17, and we'll choose as a combination. Whoops, that wasn't it. Sorry. 17. Choose as a combination 8 of them. Ooh, much bigger number. Let's enter that in and see if we've got the right answer, eh? 2, 4, 3, 1, 0, 24,310. There we go, we got it. I'm going to close this video. It looks like we need to do a part 2. Turns out this is a longer section, isn't it?